Welcome to Self Help Maths Academy. Today we're going to talk about the uniform continuity. So in the last video we have discussed about the continuity. Here we're going to talk about the uniform continuity. What is uniform continuity? Let's see that. A function f is said to be on the interval I is said to be uniformly continuous on the given interval I if for any positive number epsilon greater than 0 there exists delta, okay, such that it strictly depends on the epsilon value, okay, such that the difference between the given function f of x1 minus f of x2 is less than epsilon whenever x1 minus x2 is less than delta, where this x1 and x2 are belongs to the interval. Suppose you have the interval say I, okay, and we're talking about the uniform continuity at this interval, okay. Here what happens is we are saying that the given function is uniformly continuous on this. There exists some epsilon and epsilon greater than 0, and there exists some delta which is also greater than 0, which depends on the epsilon, okay, such that let me take some x1 which is a point of interval. Let me take x2 which is a point of an interval. Then the given function at x1 which will be f of x1, a given function at x2 which is f of x2. The difference between them is less than epsilon whenever this difference is less than delta, okay. So let us try to understand what is exactly how this uniform continuities differ from the continuous continuity. So we know that a function f is continuous at a point x naught in a given interval. For a given epsilon greater than 0, there exists delta greater than 0, such that we know f of x minus f of x naught which is less than epsilon whenever x minus x naught is less than delta, okay. Now this delta in general not only depends on epsilon here but also depends on the point x naught at which the continuity of a function f being considered. So in general here delta is what? Delta is depends on the epsilon value and x naught value. So for example, we consider say let me take an example of a function f of x equal to say x square, okay, and let us see this where x is coming from the real line, okay. So let me take our epsilon as say some 1 by 4 which is greater than 0, and let me take my point x naught is say 0, okay. Then what is your function f of x, and f of x naught will become, so your f of x is x square and f of x naught is a point 0, so 0 square will become 0. So simply it is x square which is less than 1 by 4, because this f of x minus f of x naught should be less than 1 by 4, right? So here x square is less than 1 by 4 whenever this implies x is less than 1 by 2, okay, by taking the square root on both the side. So here by taking delta equal to 1 by 2, okay, this is what we have to choose. Less than means x minus x naught, your x naught is 0 here, so yeah, this itself will be behaving as a delta. So here what happens, your f of x naught, f of x minus f of x naught is less than epsilon whenever x minus x naught is less than delta. So as per this, your delta corresponds to half and your your epsilon is equal to 1 by 4. So thus if you see your delta is 1 by 2, it works at x not equal to 0, corresponds to your epsilon corresponding to our epsilon equal to 1 by 4, which we have chosen here in the beginning, okay. Now what I'll do, let me just quickly change our x naught value. Now let us take our epsilon as 1 by 4 only, and I change my x naught slightly by 0 to 1. Then our delta equal to 1 by 2, which we got, it does not work. It does not work, okay. For instance, if you take, if we take x equal to say 1.4, if I take, then your x minus x naught becomes what? 1.4 minus x naught is 1, so this will be 0.4, which is less than half. Okay, so here no problem, but here this x minus x naught, that is satisfying. But what about f of x minus f of x naught? What happens to this function? When I take x equal to 1.4, your f of x, since it is x square, so it becomes 1.96. For x equal to 1.4, your f of x is x square, so it becomes 1.96. And since f of x x naught is 1, so this will be 1 here, so this is 0.96, which is greater than 1 by 4. This has to be less than epsilon, right? Less than epsilon means epsilon is 1 by 4. That should be less than 1 by 4. So 1 by 4 is, which is 0.25, right? So here it is 0.96. So obviously 0.96 is greater than 0.25. Hence what we got here is, here our epsilon, our delta fails. So here our delta fails. Delta is not only depending on our epsilon value, but also it depends on the x naught value. Okay, so thus what happens is, we're trying to give the motivation why we want the uniform continuity. So thus what happens, it gives for a given epsilon greater than 0, the same value of delta does not work for a different points on the of the interval. Okay, so for the different points on the interval, different points on the interval. Okay, now as you see, it worked at 0, x not equal to 0, but it does not work at x not equal to 1, right? So what we are trying to understand is, the same delta did not work for the different points which were taken on the interval. So if a continuous function f is just that given epsilon greater than 0, we can find uniform delta. We have to find now uniform delta which is greater than 0, which depends only on epsilon and not on the point x naught. Okay, so we have to find out now the uniform delta which should depends on only the value of epsilon but not on the point of x naught. Okay, which at which the continuity is considered. Okay, then we say that f is uniformly continuous. Now I think, hope you understood the difference between the continuity and the uniform continuity. So in just continuity, as we have seen in this example here, our delta was depending on the epsilon and also the x naught value, as you've seen in both the example, right? So we have to find out the uniform delta which has to depend only on our epsilon value throughout the interval. Okay, that's how we have defined our definition, uniform continuity. So we are saying that f is defined on an interval I. It is said to be uniformly continuous for even epsilon greater than 0. There exists a delta. I have specifically told this delta depends only on epsilon. Okay, delta epsilon which is greater than 0, such that the difference between these 2 points, the functional value, are less than epsilon whenever the difference between the 2 points on the interval is less than delta. Okay, so from here we have to clear with 2 points. One is, so the number 1 is, we have to say that from this, your uniform continuity, let me shortly write it as UC, uniform continuity. This is a global property. Okay, it's a global property. We talk about uniform continuity on a set. Okay, we say that the uniform continuity, it is on a set and not on not at a point, not at a single point. Okay, not at a single point. So we talk about the whole set here. That's why it is called it is the global property. On the other hand, our continuity will be a local property. It is a local property. Okay, it's a local property where we talk about the continuity at a single point. Okay, and maybe in the interval when we are saying, as you have seen, our delta depends on the epsilon as well as the given point at which you are defining our continuity. Okay, now a function is like here. Well, another thing, important thing is, a function f is not uniformly continuous. When we say a function f is not uniformly continuous on the given interval I, if when there exists some epsilon greater than 0 for which no delta works. There is no delta for a given epsilon, which says for any delta greater than 0 there exists, say x1 x2 belongs to I, such that f of x1 minus f of x2, this is greater than or equal to epsilon, and x1 minus x2 is less than delta. You can see it is not less than here, it is greater than or equal to epsilon. Then we say that the given function is not uniformly continuous. So it is simple. Okay, so in short, like I'll just give you an idea that one particular property, this implies, from here we can conclude that uniform continuity implies continuity. If the function is uniformly continuous, then on the given interval, then it is continuous on that interval. Okay, so let me take this as theorem. It says what? It says that if a function is uniformly continuous on an interval I, then it is continuous. On I. So when we have a uniform continuity at a given point, then it is always continuous. So let us prove this one. It is a simple proof. Let's start with, if f is uniformly continuous on I. Okay, then by the definition of uniform continuity, given epsilon greater than 0, there exists a delta which depends on the epsilon which is greater than 0, such that difference between f of x1 minus f of x2 is less than epsilon whenever our difference between x1 and x2 is less than delta. Okay, where your x1 x2 is coming from the interval. So this is the definition of our uniform continuity. Now what I'll do, let C be any point on I. Okay, let us consider, if I take an interval here, this is our interval, say I. So let me take a point C, any point on this interval I. Okay, now taking say x1 as some x and x2 is my point, say C, then we have, so just replacing x1 by x and x2 by C, we have our definition changed to this one, less than epsilon whenever x minus C is less than delta. Okay, so because our x1 is changed by x and x2 is changed by C. So this is nothing but what? This is nothing but the definition of continuity. F is continuous at x equal to C, but C is any point, because we have taken it is any point on the interval I. So C is any point on the interval I. Okay, so therefore F is continuous at every point of I. So since C being any point, so therefore our function f will become a continuous at every point of I. So hence f is continuous. It is simple. Okay, very simple proof, continuous on I. So this is very important. So that it implies what? If f is uniformly continuous, then given function f will be continuous at the given interval I. Okay, that is very, very important to note. Now let me give you some note here, important note. So suppose I is any interval whether open, here I may be any interval, it may be open or closed or semi-open or semi-closed. Okay, so here when I say the interval I, so it may be any interval. Okay, so the note 2 is Converse of the above theorem need not to be true. Converse of the above theorem need not be true. When I say converse of the above theorem need not be true means, what do you mean by that? Every continuous function need not to be uniformly continuous. So here every continuous function need not to be uniformly continuous. So the otherwise we know that uniformly continuous function is continuous, whereas continuous function need not to be uniformly continuous. Okay, so like we can give an example for this, and we can check. So just if you can just check with this example. If I have f of x equal to say 1 by x in the closed interval I equal to say in the closed interval ab, where a is greater than 0, is uniformly continuous. Okay, it is uniformly continuous, and it is uniformly continuous in this particular interval. But if you take the function, for example, the same function if you define from the semi-closed interval, say 0 to 1, okay, same function I'm defining in this interval from I is from 0 to 1 to r, then your function is continuous on the interval I, and here x is not equal to 0 in I, then 1 upon x will be continuous on I, but it will not be uniformly continuous. Okay, so just check this one. So this is the counter example which we can quote it for our converse is not true. Okay, but it will become uniformly continuous when you take the closed interval. All right, so this will be this function is continuous on a closed interval AB, then it becomes uniformly continuous on the closed interval AB. When you define it on this interval, it will be just continuous, but it will not be uniformly continuous. Okay, that is very important property in order to understand. Now let me take one quick example to check whether the given function is uniformly continuous or not. So let us see here. Show that the function f defined by f of x equal to x upon x plus 1 is uniformly continuous on the closed interval, say 0 to 2. So they have given that we have to show that given function f of x is uniformly continuous on this closed interval or not. So to solve this, let epsilon greater than 0 be given. Okay, now we'll take with x1 and x2 by these are be any two points of the interval 0, 2. Okay, so that your x lies between 0 and 2. Okay, whichever the points you're taking, maybe x1 lies between 0 and 2, and your x2 also lies between 0 and 2. Okay, now this implies let me add 1 on both the side. This will be 1 less than or equal to x1, which is less than or equal to 2 plus 1 will be 3. And similarly here also I'll add 1. This is 1 is less than or equal to x2, which is less than or equal to 3. Okay, so what happens is this implies, now what I do, I'll try to take, this is nothing but in this case I'm adding here also I have to add all the throughout I'm adding 1, right? So let me add it here also. Sorry. So what happens is, now this becomes your modulus of x1 plus 1 is greater than or equal to 1, because it is less, it lies between 1 and 3 means it is greater than or equal to 1. This quantity is greater than or equal to 1, and similarly here also x2 plus 1 is greater than or equal to 1. Okay, so this implies 1 over x1 plus 1 is less than or equal to 1. Just equality reverses when you take the reverse, and here also 1 divided by x2 plus 1 is less than or equal to 1. Okay, so now let me consider I want the definition of our uniform continuity. It says like this: f of x1 minus f of x2. So here, what is your f of x1? Because we have to take it in that order. Now our f of x1 is x1 upon, because f of x is x by x plus 1, so I'll take my f of x1 will be x1 upon x1 plus 1, and f of x2 will be x2 upon x2 plus 1. Okay, so this is equal to take the LCM. So here it is x1 into x2 plus 1 minus x2 into x1 plus 1 upon x1 plus 1 into x2 plus 1. Okay, so this is equal to multiplying x1 x2 plus x1 minus x1 x2 minus x2 upon x1 plus 1 x2 plus 1. So plus minus cancels. This is equal to modulus of x1 minus x2 upon x1 plus 1 x2 plus 1. Okay, so this is now if you see this value, it is as good as this x1 minus x2 divided by this value we have. So this value will be less than or equal to modulus of x1 minus x2. Okay, and this x1 minus x2, as these are the points of the interval. So since you have seen that your x1 plus 1 is greater than or equal to 1, and your x2 plus 1 is also greater than or equal to 1, so the difference between x1 and x2 will be less than epsilon, whenever you can choose your x1 minus x2 is less than delta. Okay, so therefore this implies we have got the definition of, you can see this we have started with, this we have got as less than epsilon whenever your difference between them is less than delta. This implies f is uniformly continuous on the closed interval 0, 2. Okay, so this is how you have to show that the given function is continuous in the closed interval 0, 2. Right, now let me take another example in order to check this one. Show that if suppose f of x equal to 2x upon 2x minus 1, this is uniformly continuous in the interval 1 to infinity. Okay, let's see, this is given in the interval 1 to infinity. We have to check whether the given function is uniformly continuous or not. So for this, what we do, let us start with let epsilon greater than 0 be given. Okay, then same thing, let x1 and x2 be any points in the interval 1 to infinity. Okay, so that your x1 is greater than or equal to 1 and x2 is greater than or equal to 1. All right, so then what I'll do, I'll from both the side we will subtract 1, let me multiply with the 2 on both the sides. So this will be 2 x1 is greater than or equal to, say, this will be greater than or equal to 2, and say x2 is greater than or equal to 2. Okay, let me write this as 2x1 is greater than or equal to this, let me write as 2 plus 1, and 2x2 is greater than or equal to 1 plus 1. Now subtracting on both the side with a 1, so 2x1 minus 1 is greater than or equal to 1, and 2x2 minus 1 is greater than or equal to 1. Okay, I'm subtracting with both the side with the 1. So let me take now 1 over 2x1 minus 1. If you want, you can just take them in the modulus also. So 1 upon 2x1 minus 1 is less than or equal to 1, and 1 upon 2x2 minus 1 is less than or equal to 1. Okay, now consider f of x1 minus f of x2. This is equal to, since your function is given as 2x upon 2x minus 1, so I'll take this as 2x 1 upon 2x1 minus 1, 2x2 upon 2x2 minus 1. So take the LCM and solve it. Here if you see, This will be 2x1 into 2x2 minus 1 minus 2x2 into 2x1 minus 1 upon, it is in the modulus only, then 2x1 minus 1, this is 2x2 minus 1. Okay, and here this is equal to, just multiplying, this is 4x1 x2 minus 2x1 minus 4x1 x2 plus 2x2 divided by, this is 2x1 minus 1 2x2 minus 1. Okay, now this cancels here, we are having the 2x2 minus 2x1. If you see this, we can take it as 2 times of, let me take it here itself. So 2 times of, say, x2 minus x1 upon 2x1 minus 1 and 2x2 minus 1. Okay, yeah. So this one, if you observe, this is nothing but what this quantity, this whole quantity will be less than or equal to 2 times of modulus of, because since it is in a modulus, whether you take x1 minus x2 or x2 minus x1 doesn't make difference. So x1 minus x2, and this is, say, less than epsilon. Okay, so whenever, so since if you observe, this is 2 times of x1 minus x2 is less than epsilon, implies x1 minus x2 will be less than epsilon by 2. Okay, so here choose your delta as epsilon by 2. As you know, you can see your delta is depending on epsilon here. So hence we got started with f of x1 minus f of x2, which is less than epsilon whenever your x1 minus x2 is less than delta. So this is the definition of what? Uniform continuous. So hence we say that f of x is uniformly continuous. Okay, uniformly continuous. This is how you will be solving the examples on the uniform continuity. When it comes to the examples, we have to first try to understand where the interval is, and we have to find out those points, and then you will apply it for the definition. Okay, I think this is all for the uniform continuity. Maybe in the next video we'll discuss some different topics. Okay, till then, take care, guys.